Hey everyone, and welcome to this explainer. Today, we have a truly fascinating topic lined up for you. We're going to pull back the curtain and uncover the real foundations of deductive artificial intelligence. So let's just dive right into it. When most of us hear AI today, we immediately picture these massive neural networks, generative models, chatbots, the whole shebang. But there is actually a whole other side to the AI coin. We're talking about an older, mathematically rigorous paradigm that is built entirely on explicit rules, pure logic, and readable symbols. It's the absolute bedrock of deductive AI, and honestly, understanding this is the key to building systems that we can actually trust.
So I want you to let this sink in for just a second. What if an AI could mathematically guarantee that it will never, ever make a mistake? Pretty wild, right? We live in a world where modern neural networks are undeniably powerful, but they're also incredibly unpredictable. They hallucinate, they will confidently give us completely wrong answers. But what if we contrast that unpredictable nature with the absolute certainty of formal deductive logic? Well, that is the exact promise of symbolic AI. We're talking about a system where if the premises are true and the rules are followed, the conclusion is undeniably provably correct. No guessing involved.
And this idea right here brilliantly illustrates where it all started. AI pioneers Alan Newell and Herbert A. Simon formulated what's known as the physical symbol system hypothesis. Basically, early computer scientists believed that intelligence wasn't about some mysterious brain waves or magic. It was purely about manipulating readable symbols according to very strict rules. Think about it like a giant puzzle, like algebra or a game of chess. The symbols represent reality, and the rules strictly dictate how you can move them around. If you can build a physical system that manipulates these symbols logically, Newell and Simon argued that you literally have everything you need to create general intelligence. So because of this, there's a very clear separation between the two major camps of AI research. On one side, we have connectionist AI. That's your modern deep learning, which automatically learns from vast amounts of data, but scatters all that knowledge across a totally opaque network of artificial neurons. It's basically a black box. But on the other side, we have symbolic AI, sometimes called good old-fashioned AI or GoFi, and its strengths are totally different. It uses human-readable symbols, manually encoded rules, logical reasoning, and it offers total explainability. It operates using expert systems and logical programming languages like Prolog, relying on strict if-then pairings. If X happens, then do Y. It is perfectly transparent. Section 1. Human Rules as Symbolic Systems. Now, before we even had computers, humanity had already created its own massive, complex symbolic systems. You could argue that human law is the original symbolic system. It operates on strict, rule-based logic designed to safeguard human intent and organize society. For a really tangible example of this, let's look at the Berne Convention, specifically Article 6 bis. This is an international copyright treaty that establishes what are known as moral rights for authors. It lays down strict logical conditions. It says an author has the fundamental right to claim authorship, which is known as paternity, and the right to object to any distortion or mutilation of their work, known as integrity. These rules essentially act as a formal specification. They operate completely independently of economic rights to protect the author's honor and reputation. It's a classic if-then expert system. It's just written for human judges instead of computer processors. But, here is the catch with rigid frameworks. When you try to apply strict symbolic rules across different cultures, they inevitably clash with real-world variations. For instance, the United States joined the Berne Convention, but they fundamentally struggled with those specific moral rights. And why is that? Well, because American copyright law is heavily focused on economic injury and property rights, rather than the European focus on an author's honor and reputation. So a rule that works perfectly in one environment might just completely fail to compute in another. Section 2. Formal verification guarantees truth. So the crucial point here is that while human law is a really powerful symbolic system, it's still open to interpretation and culture clashes. So what happens when we transition from human legal frameworks to actual computer code? Well, this brings us to a highly complex yet incredibly vital process called formal verification. This is where we translate strict rules into mathematically provable software. If we want systems, think core financial networks, aviation controls, medical devices, things that absolutely cannot fail, we use this three-step pipeline. Step 1 is the spec. That's a rigorous mathematical formalization of human intent. It dictates exactly what a program is allowed to do and what it must never do. Step 2 is the code, which is just the actual executable instructions. And step 3 is the proof. This is a mathematical argument demonstrating beyond any shadow of a doubt that the code perfectly satisfies the spec across all possible inputs. It replaces let's test it and see with absolute mathematical certainty.
Let's look at the incredible power of deductive reasoning in action through two legendary examples in computer science, the CEL4 microkernel and the CompCert compiler. CEL4 is the first ever general-purpose operating system kernel to be fully formally verified. Through mathematical proofs, its creators guaranteed functional correctness and the absolute absence of bugs in its 8,700 lines of C code. 0 bugs. CompCert does something really similar for compiling code, ensuring that the generated machine code behaves exactly as prescribed. In a world where AI-powered hackers are moving way faster than human security teams ever could, these verified systems provide a foundation of defensible certainty.
But there is a massive catch. 20. That is how many person-years of grueling, mind-numbing manual labor it took just to verify those 8,700 lines of the CEL4 microkernel. 20 years of effort for a relatively tiny piece of software. This perfectly highlights the massive cost of pure symbolic logic. Historically, formal verification has required writing the spec and much of the proof entirely by hand. That makes it so impossibly expensive that it really only makes sense for the most critical cloud infrastructure.
Section 3. The problem with messy reality.
And this leads us to the fatal flaw of symbolic AI and rigid rule-based systems. They simply struggle to handle the unpredictable, unstructured variations of the real world. We're kind of stuck between a rock and a hard place here. Manual, formal verification is tedious, incredibly expensive, and doesn't scale at all. So you might be thinking, hey, let's just use modern AI. Let's use large language models to do the verification. But using LLMs for this has some really significant drawbacks. They are fast and scalable, for sure, but they're also hallucination prone. They completely lack true abstract deductive reasoning. An LLM operates by pattern matching and just generating the most likely next word. It doesn't actually know the strict logical rules required to mathematically prove a system is secure. If we rely purely on LLMs, companies are going to spend way more time fixing LLM-generated code than they ever spent writing it in the first place.
Section 4, Neurosymbolic AI bridges the gap.
But don't worry, there is a resolution to our story here. We are now entering an era of synthesis, where we're taking the best of both AI paradigms to fix the flaws of each. Enter neurosymbolic AI. This is a hybrid approach, and let me tell you, it is gaining massive attention right now. It integrates the incredible pattern recognition and adaptability of neural networks with the strict logical, explainable reasoning of symbolic AI. It basically acts as a bridge. The neural network part can process messy, unstructured, real-world data, like images or everyday language, while the symbolic part applies clear reasoning rules. This gives us auditable, white box explanations for the AI's decisions. It solves the black box problem while totally maintaining flexibility. It's a real game changer. And the cool part is we are already seeing this synthesis revolutionize formal verification. Modern vericoding pipelines are starting to use what are called energy-based reasoning models, or EBRMs. In this setup, a large language model acts as the user interface. It takes our messy, ambiguous human requirements and translates them. Then the EBRM steps in. It handles the highly constrained logical search, dynamically mapping inputs to a latent space to align the spec, the code, and the proof, generating mathematically verified code automatically. This is exactly how we solve that crazy 20-person-year bottleneck. We use connectionist AI to understand the world and symbolic AI to prove the math. To wrap things up, I want to leave you with this final, somewhat provocative thought. Neurosymbolic AI is pointing us straight toward artificial general intelligence. If an AI system can eventually observe the messy reality of our world through neural networks and then automatically generate its own strict symbolic rules from that raw data, will it finally bridge that common sense gap that has limited AI for decades? The convergence of connectionist and symbolic systems might just be the actual key to true human-like reasoning. Thank you so much for joining me on this explainer, and keep questioning the logic behind the code.